Hello everybody, my name is Samuel Horvath and I'm a PhD student at KAUST. This is my presentation for the Machine Learning Summer School 2020 that was supposed to take place in Tübingen. The title of my presentation is Natural Compression for Distributed Deep Learning, which is a joint work with my collaborators Elton, Ludovic, Atal, Marco, and my supervisor, Peter. Let me start with an introduction of distributed learning with n nodes, which are also referred to as slaves or workers, and one master node, also referred to as center server, which is used for aggregation. This is a typical machine learning training scenario, which arises in several situations. For instance, imagine one wants to train a deep learning model and has access to a large data set, which can't be possibly stored just on one machine. The several machines are needed. Another possibility is that one has access to significant computational resources represented by our nodes, and in order to fully exploit these resources, each node holds part or the full dataset. Somehow different but very relevant example is federated learning, where each node represents one client, which owns its own data, which are not shared among other nodes due to privacy requirements. In distributed training, every optimization step proceeds in the following way. At the beginning, each node has the same copy of current solution and computes a stochastic gradient based on its local data. These gradients are then transmitted to the center server and aggregated. After the aggregation step, the local updates is sent back to workers, which perform one SGD step based on this global update. Unfortunately, there is a significant issue with this approach. The problem is that for typical distributed computing architectures, the time spent on communication is significantly longer than one spent on computation. This is a major bottleneck and limiting factor as it prevents efficient exploitation of computational resources. For instance, doubling number of machines might lead to actually increase in overall time rather than its expected reduction by half. Thankfully, several remedies were proposed in the literature where the first line of work proposed to increase local computation before communication, which can be achieved by either increasing mini-batch size, or one can define local problems for each worker, or we reduce frequency of communication, which is possible via incorporating local updates. Another orthogonal approach to this is to compress message before its communication. For instance, in our case, compression of gradient vectors. This can be achieved using either quantization or sparsification. There is also a third approach, and this is to modify architecture in order to allow for faster aggregation. For instance, it was proposed to replace center server by programmable switch. In this talk, our main focus is the second approach, and we will slightly touch the last one. Right now, let's just look at the algorithmic change of the second approach. Similarly to what we mentioned before, every optimization step begins with each worker having the same copy of solution, and it computes local stochastic gradient based on the local data. Instead of communicating the full vector, its compressed version is used. The master node provides aggregation, and the resulting vector is compressed again before it's sent back to the workers, which perform one SGD step. After this introduction of compressed parallel distributed optimization framework, we are ready to proceed with contributions of our work. First, we propose new compression operators, which are based on a randomized binary rounding scheme. We show that this can be efficiently implemented due to their natural compatibility with binary floating point types. In addition, our methods can be used in a combination with other compression operators to further enhance their performance. We also provide theoretical guarantees for a wide class of compression operators, which are defined in the next slide in a non-convex setting. And we show that our methods are superior to all commonly used compression operators, and unlike the other methods, they bring provable speed up over distributed optimization with no compression. Yeah, our theoretic findings are also supported by experimental evaluation. As the last contribution, we also showed that our mechanisms are first, which can provably work with in-network aggregation. In this slide, I will introduce very general class of compression operators for which we analyze compressed distributed stochastic gradient descent, SGD. The first equality implies that in average, the true update is communicated, and the inequality guarantees that the variance of the second moment is bounded with respect to the magnitude of X. Roughly said, in our work, we show that variance negatively affects the number of iterations, and one needs approximately omega plus one more iteration to reach the same quality solution as non-compressed algorithm in the non-convex setting. Let's now move to our proposed compression. The first one is natural compression, which operates in the following way. For every real number, this compression rounds it to either closest bigger or smaller power of 2 with probability proportional inverse to its distance. Here is an example. So for the number 2.5, the closest powers are 4 and 2, and the corresponding probabilities are 1/4 and 3/4, respectively. The reason why we call this compression natural is because there is no need for any computation if we have access to float representation. As shown here in our example, sign is preserved, and we either increase exponent with probability that corresponds to mantissa by 1, or we keep it the same otherwise. If our input is a vector, then natural compression is applied element-wise. We can see that for our compression, there is no need to communicate mantissa, which means that we communicate 4 times less, while we show in our paper that the worst case increase in number of iteration is at most 12.5%. For the more drastic compression, we propose to use natural dithering, which operates by communicating the sign of the vector input, its p-norm, and low precision version of natural compression parameterized by the number of level S applied to the normalized version of the input vector, for which, as one can see, all elements lay in the 0-1 interval. This low precision compression operates in the same way as natural compression, with the only difference is that if the input is smaller than 2 to the power of minus s, it is either rounded to its value or 0. The display image right here shows our rounding scheme for s is equal to 2. And here, as you can see, after 2 to the power minus 2, there are no more levels, just only level 0. Yeah. In our work, we showed that this procedure is exponentially better than standard dithering operator, which was considered as the state-of-the-art compression. To support our theoretic findings, we conclude several experiments. In the first one, we showed that adding natural compression to training has almost no effect on the convergence of ResNet 50 for ImageNet dataset, while significantly reducing the communication. We also showed that natural dithering reaches the same performance as a standard dithering, while it only needs log amount of levels comparing to standard dithering, thus significantly reducing the size of the messages that need to be communicated. Thank you for watching, and for more details, I would like to refer you to our page.